For over 2 decades, Toyota has been a pioneer in electrified mobility, leading the way with innovative, efficient, and capable powertrains. In this video, we'll explore Toyota's full range of electrified systems, from hybrids and plug-in hybrids to battery electric and fuel cell vehicles, each engineered to meet the needs of today's drivers while helping build a cleaner tomorrow. Toyota helped spark the electrification revolution in 1997 with the debut of its hybrid electric powertrain, proving its practicality for everyday passenger vehicles. Since then, the company has expanded its hybrid EV lineup to include numerous models that have sold by the millions worldwide. Today, Toyota's latest hybrid EV system, also known as the Toyota Hybrid System, or THS, is an evolution of that original series parallel design, where the wheels can be driven by the gas engine or the electric motor, or both, and it has been further refined to provide better performance and efficiency. Above all, the hybrid EV THS system never needs to be plugged in, since it completely charges the hybrid EV battery via engine power or regenerative braking. Plus, its components, including the hybrid EV battery, have been designed with longevity, durability, and reliability in mind. To really appreciate how the powertrains in these vehicles help reduce carbon emissions, it's important to understand what's happening under the hood, learn how they operate, and take a closer look at the entire process from the moment the start button is pressed. Unlike a traditional gas-powered vehicle that cranks a starter motor to get things going, a hybrid EV start button first powers up the system's onboard computers, the electronic control units. Like virtually all automotive systems, these ECUs operate on the 12-volt battery circuit, which also powers vehicle lighting, windows, door locks, and similar features. This explains why you'll find a typical 12-volt automotive battery on every Toyota hybrid EV. Once online, these ECUs check things like the hybrid EV battery status, engine temperature, and ambient temperature. They also manage some of the most crucial components in the vehicle, the system main relays. These relays are next in line and do the heavy lifting of sending hybrid EV battery power to the components that utilize high voltage, and ensuring the battery power is switched on in a safe manner when the vehicle starts, to avoid spiking any element of the system. For safety, if any fault or collision is detected, these relays are designed to immediately power down, isolating the hybrid EV battery while shutting off the high voltage cables, which are color-coded in bright orange. Once the ECUs are up and running, the hybrid EV battery power is sent to the inverter converter. This device controls the high voltage flow to and from the motor generators and the high voltage battery, and maintains the charge on the 12-volt battery anytime the vehicle is running. The motor generators, as the name implies, works as both a motor, providing power when needed, or a generator to charge the hybrid EV battery. Each plays a critical role in how the hybrid EV system works. Motor Generator 1, or MG1, is located directly behind the engine, and when used as a motor, starts the engine on demand anytime it's needed. Because MG1 is much more powerful than a traditional starter motor, it doesn't require a gear drive and is able to start the engine silently. This is the reason you never hear the typical starter sound on a Toyota hybrid EV. Once the engine is running, MG1 is used as a generator and charges the hybrid EV battery. A major key to how the hybrid EV system works is a planetary gear set that acts as a power split device. This is used like a continuously variable transmission to manage the output between the engine and the motor generator 2. Parallel power output from the engine and MG2 work together or separately to power the wheels when accelerating and cruising. MG2 also acts as a generator when the brakes are applied or when coasting to capture the energy from the vehicle's forward momentum and charge the hybrid EV battery anytime the vehicle slows down. This two-motor hybrid EV design also takes advantage of Atkinson cycle cam timing, which essentially means the intake valves stay open slightly longer and create less pressure in the cylinders. This design makes for exceptional efficiency and low tailpipe emissions, but the trade-off is a relative lack of power. That's why it works alongside Motor Generator 2 to produce a combined pool of power, helping provide both exceptional efficiency and good power response, the best of both worlds. So, what if you want to make a front-wheel drive hybrid EV an all-wheel drive vehicle? It's surprisingly simple. Unlike traditional all-wheel drive vehicles that use a mechanical drive shaft to distribute the power from the engine out to all four wheels, Toyota engineers simply add an additional third motor generator directly to the rear, right in between the wheels. This explains why it's called motor generator rear. This standalone unit has no mechanical connection to the rest of the drivetrain, but still helps add extra traction, capability, and power at the rear when it's needed, and like MG2, generates power for the hybrid EV battery when coasting or braking. So that's a quick look at the Toyota hybrid system that's found in so many Toyota vehicles. Building on the foundation of hybrid technology, Toyota takes efficiency even further with its plug-in hybrid system. Now let's find out how the plug-in hybrid EV powertrain functions and how it's different from a hybrid EV and a battery electric vehicle. Toyota's plug-in hybrid EVs built upon the legendary THS architecture. They feature a similar layout with a gas engine up front coupled to two electric motors. Additionally, vehicles with electronic on-demand all-wheel drive add a third electric motor on the rear axle. Plug-in hybrid EVs enhance the capabilities of the venerable Toyota hybrid EV system, resulting in improved performance. Like the standard Toyota hybrid system, Motor Generator 1 works as a starter for the engine and recharges the battery when the engine is running. Motor Generator 2, on the other hand, recharges the battery when the vehicle is coasting or during braking. It powers the wheels on its own, or alongside the gasoline engine in normal driving conditions. In plug-in hybrid EVs, Motor Generator 2 is also used for high-speed driving in all-electric mode. Finally, if equipped, plug-in hybrid EVs use Motor Generator rear when driving in all-electric mode, resulting in additional traction and power during zero-emissions operation. Another major distinguishing factor in plug-in hybrid EVs is the battery, specifically its capacity. Vehicles powered by the Toyota hybrid EV system already use a high-voltage battery pack to power their electric drive system. But plug-in hybrid EVs have an even higher capacity battery unit that allows for their extended EV mode driving. In fact, when charged up, plug-in hybrid EVs can drive for miles, up to highway speeds, on electric power alone. Perfect for a zero-emissions daily commute. However, if the battery charge level gets low from either extended range driving or if the vehicle hasn't been plugged in, the plug-in hybrid EV powertrain continues to operate normally. The vehicle just automatically reverts to hybrid mode instead, with the gas engine coming online to support the electric drive system. This flexibility is the whole beauty of Toyota's plug-in hybrid EVs. They can offer the advanced convenience of all-electric driving for shorter trips and everyday commutes, or simply operate as fuel-efficient hybrids when that EV mode isn't available. Additionally, plug-in hybrid EVs aren't only about efficiency. With the added battery capacity and the electric motors working together with the gasoline engine, these are some of the quickest accelerating vehicles in the Toyota lineup. Like the Toyota hybrid EV system, plug-in hybrid EVs use a high-voltage battery designed with longevity, durability, and reliability in mind. And, like a battery EV, they also include an onboard charger and a charging cable. This allows owners to simply plug the vehicle into a standard wall outlet to recharge, or a level 2, 240-volt charger for quicker charge times. The onboard charger converts the incoming AC electrical current to DC current, which is what the battery uses to store power and power the electric motors. This ability to plug in enables plug-in hybrid EVs to charge the battery beyond what a standard hybrid EV system would do through self-charging. That said, plug-in hybrid EVs will still self-charge the battery when needed, just at the level needed to maintain hybrid operation instead of all electric. That means the gas engine recharges the battery when needed, and the vehicle goes into all-electric operation during low-speed driving, traveling downhill, or coasting, just like how the Toyota hybrid EV system operates. So, while there are certainly benefits to plugging a plug-in hybrid EV in, it isn't required, providing peace of mind if a charger is not available. It really combines the best of a battery EV and a hybrid EV, all in one cleverly engineered vehicle. So that's a quick look at Toyota's plug-in hybrid EV system and how it builds on the legendary Toyota hybrid EV system by adding an extra layer of capability, performance, and versatility. For drivers seeking even more performance without sacrificing efficiency, Toyota introduced Hybrid Max, a powertrain that pushes hybrid capabilities to new heights. It's a single-motor, parallel hybrid platform engineered for driving enthusiasts. Hybrid Max delivers excellent power, efficiency, and a healthy dose of electrified fun for next-level driving excitement. Let's take a closer look at how this is accomplished. The Hybrid Max EV system starts up much like the Toyota Hybrid EV system, or THS, with a push-button start that fires up the onboard computers, also known as ECUs, that regulate and control the hybrid EV system. As we covered in the previous section, this explains why you'll find a typical automotive battery on every Toyota hybrid EV. These ECUs operate on the 12-volt circuit, which also powers vehicle lighting, windows, door locks, and similar features. Once all systems are online, that's when Toyota's Hybrid Max EV system starts to showcase what sets it apart. Unlike THS, where each motor generator has independent roles, the parallel hybrid system's single motor helps with a range of duties while getting down the road, like engine startup, energy regeneration when coasting or braking, and assisting the engine with power delivery to the wheels, making for a truly efficient setup and ultra-quiet startups. The hybrid EV battery, on the other hand, powers up via the system main relays just like on THS. These send hybrid EV battery power to components that use high voltage and ensure that battery power is switch-on safety when starting the vehicle to avoid spiking any element of the system. If a fault or collision is detected, the system main relays power down for safety, isolating the hybrid EV battery while shutting off the high-voltage cables, which are color-coded in bright orange. Unlike THS, that relies on a power split device to manage the output that drives the wheels, the Hybrid Max EV system uses a single motor generator connected to a traditional 6-speed automatic transmission via a unique wet start clutch in lieu of a traditional torque converter for exceptionally responsive power delivery. A K0 clutch is also used to disconnect the engine from the transmission. Both clutches work together to allow the motor generator to start the engine, charge the battery, and power the wheels. Hybrid Max EV's focus on performance is most evident with the type of internal combustion engine it's paired with and how it operates. Unlike the naturally aspirated engines paired with THS, which run on the efficiency-focused Atkinson cycle, a powerful turbocharged engine operating on a conventional combustion cycle is used instead. This parallel hybrid system brings the power on from both sources nearly all the time, instead of frequently switching between the electric motor, gas engine, or a mix of both as needed to deliver maximum performance while still offering great efficiency. As a result, drivers experience smooth, energetic performance, realizing the true power of the Hybrid Max EV system. That's not all. Toyota's new bipolar nickel metal hydride battery also plays a major role in this performance story. Unlike a traditional nickel metal hydride battery, the bipolar unit doesn't require the current to pass through terminals as it goes through every cell in the pack. This results in fewer components being used and decreased internal resistance, allowing larger electrical currents to flow through the pack, increasing overall power output and improving vehicle responsiveness. But this is only half of the Hybrid Max EV performance story. Power is nothing without control, and Hybrid Max EV delivers power to all four wheels via a new e-axle system, which delivers nearly 30% more power to the rear wheels than Toyota's electronic on-demand all-wheel drive system. This new e-axle not only provides excellent traction when conditions get rough or slippery, but it's proactive, delivering power to the rear wheels as needed, even when conditions are ideal. By sending more power to the rear, the front tires utilize the contact patch more effectively to steer the car on the driver's intended line, delivering more precise cornering and enhancing the fun-to-drive factor that Hybrid Max EV is all about. So that's a close look at Toyota's Hybrid Max EV system and the clever engineering that elevates both efficiency and power in one incredibly fun-to-drive package. When power and rugged performance are essential, Toyota raises the bar again with iForce Max, a hybrid EV system purpose-built for trucks and SUVs, designed to handle towing and off-road challenges without sacrificing fuel efficiency. On startup, a push-button start fires up the onboard computers, also known as ECUs, which regulate and control the hybrid system. Once the ECUs are on, the system main relays ensure that the hybrid battery powers up safely and isolated in case of a fault or accident. Additionally, like all vehicles, a typical 12-volt automotive battery system is equipped on vehicles powered by the iForce Max EV powertrain, which controls the lighting, windows, door locks, and similar features. What sets iForce Max EV apart is how the components are laid out. Toyota engineers place the electric motor between the internal combustion engine and a conventional automatic transmission, allowing them to retain the rugged drivetrain components necessary for demanding towing and off-road use. Like other Toyota hybrid EV systems, iForce Max EV utilizes a motor generator that works with the internal combustion engine to drive the wheels, as well as regenerate electricity when coasting or braking for maximum efficiency. The hybrid EV battery system is electronically connected to the electric motor, giving it the energy needed to generate the system's incredible power, supplementing the internal combustion engine in points where it may not be at its peak output. Both sources work together to provide plenty of torque that's easily accessible, making iForce Max EV ideal for demanding tasks. Unlike the Toyota hybrid EV system, which uses a unique continuously variable transmission, the iForce Max EV system utilizes a rugged conventional automatic transmission. This setup retains the capability and toughness to handle rigorous driving situations and the same level of gear selection control that drivers would find in a conventional drivetrain, retaining the capabilities truck owners need. Unlike other electrified all-wheel drive vehicles in Toyota's lineup, which use an electric motor to power the rear wheels, the iForce Max EV system employs a mechanical connection to link the internal combustion engine, motor generator, gearbox, and driven wheels. To achieve that, a drive shaft is utilized, enabling power to flow from the powertrain to the rear wheels. Furthermore, a 2-speed transfer case with a low range is incorporated on 4-wheel drive equipped models to handle the demands of off-road use. Plus, a strong rear axle is utilized for towing and hauling. So that's a quick look at Toyota's potent iForce Max hybrid EV system and how it uses electrification to enhance the performance and capability of Toyota trucks and SUVs. With iForce Max EV, drivers can expect legendary capability, backed by Toyota's reputation for quality, durability, and reliability. Building on its hybrid leadership, Toyota takes electrification further with fully battery electric systems that deliver instant torque, quiet operation, and zero emissions, all in a highly versatile package. Let's take a closer look at how this next-generation EV powertrain operates. Unlike a hybrid EV, plug-in hybrid EV, or fuel cell EV system, which include a combustion engine or a fuel cell stack and a fuel tank, a battery electric powertrain makes use of a single or multiple electric motors and a high-capacity battery. Press the push-button start and the system comes alive much like Toyota's other electrified systems, activating the onboard computers, known as ECUs, that regulate and control the powertrain. These ECUs also control and maintain charge on the 12-volt battery located under the hood, which is used to power vehicle lighting, windows, door locks, and other similar features. On the other hand, the high-capacity battery powers up via the system's main relays. These send power to components that require high voltage, ensuring battery power is switched on safely upon vehicle startup to avoid spiking any element of the system. In the event that a fault or collision is detected, the system main relays power down safely to isolate the high-capacity battery and turn off the high-voltage cables, which are color-coded in bright orange. Unlike hybrid EVs and plug-in hybrid EVs, battery electric powertrains use motor generators exclusively for motivation. Since there is no internal combustion engine or fuel cell stack, motor generators are the only source of motivation. In two-wheel drive vehicles, one motor generator powers the front wheels, while all-wheel drive models use two of them, one mounted on each axle. This means that each electric motor powers the front and rear independently, allowing for improved power management at each wheel. Unlike an internal combustion engine, which generates power across a power band, electric motors respond right away when the driver presses the accelerator and are able to generate maximum torque from a complete standstill, resulting in smooth, lag-free power delivery. Equipping a battery EV with two electric motors not only provides extra power, it also helps better manage traction through the precise control of power delivery when driving in inclement weather conditions. Plus, the power from the second electric motor, which is routed through the rear wheels, enhances the vehicle's handling and grip in the dry. Finally, just like Toyota's other electrified powertrains, battery EVs are capable of energy regeneration. When coasting or braking, the traction motors work as generators, recapturing wasted energy and turning it into electricity, which is then stored within the high-capacity battery. In addition to the normal drive selection options, Toyota battery EVs have a regeneration boost mode, which provides increased regenerative braking and greater deceleration levels when lifting off the accelerator pedal, resulting in more energy being recaptured while reducing the need for the driver to press the brake pedal to slow the vehicle down. Battery EVs are further differentiated when it comes to charging. Like plug-in hybrid EVs, they can be charged via a level 1 charger like a 120-volt household outlet or a level 2 AC charger that outputs 240 volts. An onboard charger converts alternating current to direct current, allowing the battery to be replenished to 100% charge overnight through a level 2 charger. For faster charging times, battery EVs can use level 3 DC fast chargers found in public spaces. Since the onboard charger doesn't need to convert electricity to direct current, the battery can be recharged quickly, usually reaching 80% in an hour or less under ideal conditions. However, electricity intake slows down after 80% to further preserve the battery's durability. So that's a closer look at Toyota's battery electric powertrain and how it combines responsive performance with zero emissions. For those seeking zero emissions without the weight, Toyota's fuel cell electric vehicles provide a compelling hydrogen-powered solution. True to Toyota's innovative spirit, this system combines the quick refueling of a gas-powered car with the smooth, silent performance of an all-electric drive. Fuel cell electric powertrains are unique in that they generate their own electricity using hydrogen as a fuel. This is achieved via a fuel cell stack, which is where a chemical reaction occurs between oxygen from the air and the hydrogen fuel stored in the storage tanks. Once the reaction combines the oxygen and hydrogen, electricity is produced, with water being the only byproduct. Like Toyota's other electrified powertrains, the fuel cell EV system starts quietly and activates the onboard computers or ECUs. These ECUs operate on the 12-volt system that also powers vehicle lighting, windows, door locks, and other similar features. This explains why every electrified Toyota vehicle uses a typical 12-volt battery. These ECUs also control the system main relays and helps ensure the high-voltage system is switched on safely and doesn't spike any element of the system. In case of a fault or collision, the system main relays power down to safely isolate the high-voltage battery and high-voltage cables, the latter of which are color-coded in bright orange. Once in operation, the fuel cell electric powertrain operates similarly to a battery electric one. Power comes on right away thanks to the motor generator, which generates its peak torque nearly instantaneously the moment the driver puts their foot down on the accelerator pedal. The result? Smooth acceleration and abundant power. Just like Toyota's other electrified powertrains, the fuel cell EV system features regenerative braking. This means it uses the motor generator to recover otherwise wasted energy, turning it into electricity when braking or coasting. That is then stored within the high-voltage battery, which serves as a buffer between the fuel cell stack and the electric motor. The advantage of the fuel cell EV powertrain extends beyond its zero-emissions power generation. It combines the response and exhilarating acceleration of a battery electric vehicle with refuel times that are nearly as short as that of a gasoline-powered vehicle. In fact, fuel cell EVs can be refueled in approximately 5 minutes, allowing them to get back on the road sooner. And thanks to a cruising range that rivals or exceeds most gasoline-powered vehicles, drivers can go the distance. Best of all, this powertrain is easily adaptable to other vehicle applications. Using the same fuel cell EV system found in the Toyota Mirai, Toyota engineers scaled up the technology, producing a drivetrain capable of powering Class 8 heavy-duty semi-trucks. So that's an up-close look at fuel cell EV systems, one of the innovative powertrains that form Toyota's Electrified lineup. From hybrid and plug-in systems to battery electric and fuel cell technologies, Toyota's electrified powertrains are built to perform, built to last, and built for the future. To learn more about Toyota's commitment to sustainable mobility, visit toyota.com/electrified.